on 7th October. I couldn't be recorded due to some issue. So I will start the class today. Next class, we specifically dealt with the doubts that were there uh, by the students. So they mailed me personally. So uh, in the extra class, actual extra class, my Manisha joined. So if you want to know further beyond this extra class, there will be no classes. So if you want to understand or if you have any doubt on the particular topic, you can mail me. So I will just start the class. So frequency flat selective coding was one of the topic in week 11 and 12. So I'll start from that. So basically, the frame synchronization and the frequency recovery process presented in chapter 5 and 6 procedures presented in chapter 5 and 6 are done without regard to any distortion due to intersymbol interference resulting from frequency selective fading. So as in the class we saw, this is also called a flat fading, where we have distortion other than this particular bandwidth. So frequency selective or flat fading. So whereas the flat fading is one of the different type. Okay, frequency where the flat fading channel only imparts a gain in a phase, where and a frequency selective fading channel performs convolution and thus may impart gain in a phase that varies as a function of time. So in this frequency selective fading is another form of flat fading where the gain in a phase is a function of time. Okay. The insertion of the channel's filters response H prime K in the baseband model implies that the net effect of the pulse-shaped filter and the channel filter and the receiver's mass filter is no longer an ideal Nyquist pulse, just an aqueous pulse. So we can see the eye diagram here as well. So this is BPSK eye diagram for no ISI and this is the ISI. So intersymbol interference is no there, not there, where you're having, so they are so much converging and overlapping happens in the signal. So this was not covered by class, but I will tell you the one thing which is very important. This is a linear equalizer for a frequency selective fading. Okay, so you have the pilot as input in channel, and then that got added to the noise, and it is then passed to the equalizer, and you have the skew bar of n, and then it is also sent as an error from the delayed version because it is showing that whatever you are getting as input as an pilot, and if you are delaying it, and you are getting the output, that is that, and this is called linear equalizer for a frequency selective fading. So this is one of the good thing that we can see. Another thing that I would like to see both all of you to go through uh, these questions. Okay, that's it for the frequency selective fading. And there were some commands: save, load, path, packet detector, and make balance.m. These codes I will upload in the drive. Please go through that. But these all are covered. And this is the one of the good thing that we can see. There's a communication laboratory mobile app. So here you can see the acoustic transmitter and the settings were there, the hello data and the transmit carrier. So the carrier frequency was 2000 hertz. Okay. And the samples per second was a 110. Excess bandwidth was a 0.5 and the pulse half width is 5. and the constellation BPSK was kept. So you can also change something, and this was one of the mobile app we saw. So these are the inputs: text or tone, FC, upsampling factor, D, alpha, M, pilots. Constellation size will be different for BPSK and the QPSK, as you know. Upsampling, we can change the sampling rate, or then we can increase the sampling rate. In that case, this is the upsampling. Okay. And the app can be opened for the Apple devices, like a version of uh, Android device is also available. Not only. So I'll just show you acoustic quadrature amplitude modulator transmitter. So go to the Play Store. App name is, so basically I can't find it, but it's fine. You can see some output here. Frequency recovery were also covered. Now I'll go to some questions that you guys asked as a doubt to me. Okay. So detailed solution, if we start from the week 5, because there were some questions from week 5, I can see here. So they were having problems related to matrices. So I'll just go cover some matrices problem, auto covariance and how it looks like. So I explained that also, that the auto covariance function of a random process defined as EXN1 X star N2 minus EN1 X star N1. Okay, like that you can remember. Okay, and when the random process is becomes when the random variable becomes a function of another independent variable, then it is called a random process. And in random process, we have white sense stationary, non-stationary. Okay, the types of random variable, random processes. So how what type of noise is WSS. Okay, and whenever we have the correlation, then we calculate using correlation symbol. Whenever we want the output of a linear system, then it is called as a convolution. Okay, uh, otherwise correlation is calculated for finding similarity between two signals, and convolution is calculated for getting the output of a LTI system. So that's the only thing. Okay, and in week 5, uh, what is the process for the for stationary in the white sense, when the uh, when both the mean function and the autocorrelation functions are independent over time. Because it is stationary in the sense that whenever you are having a graph like this, it is not changing. Okay, so you are having x t plus delta is equals to xt, where x can be autocorrelation and mean function. Okay, I think there's a problem. There was a doubt on this. So Gaussian process can be completely characterized with mean and covariant function. That is true. And yes, so week 5 doubt is clear. I covered the same in live session as well. That didn't get recorded. Is some issue. And there was questions from this part, discrete time equivalent system. So whenever you do T is equals to NTS, and TS is actually the sampling period. Okay. In that case, you are turning the analog system. I'm talking about system to digital system. You remember that, and all your problem will be solved. So whenever in question you see somewhere, uh, uh, you have learned something or you have applied something to analog, and when it comes to digital, you get confused and you are having anxiety and you come up with wrong answers. Okay, so in that case, you replace every T with NTS, where N is a number of samples and T is a sampling period. Because why? Because in digital system, you're having the samples. You're considering the samples. Samples are considered as a form of set. So suppose this is the analog. Okay. So you are taking samples as 1, 2, 3, like that. And T is the sampling period or time. Okay. So here also it is like that. Okay, you're taking discrete time impulse response. So here you are having these samples. And energy power, again, the same doubt raised by Ashutosh, I guess. I have the mail. I'll check. Check. So Ashutosh asked that while calculating power, why we are taking average and while calculating energy, why we are calculating for the whole time samples. So very good question. But don't you think that for calculating power, you need a periodic signal? You can't calculate power for the energy signal. As you can see here, I have made properly the difference between energy and the power signal. So power signal is a signal which is periodic in nature. So you can't calculate for the thing that is getting periodic. Yeah, I agree that it's infinite. So you're thinking, but here also we are doing the infinite sum. We remember T is tends to infinity at the sum. Yeah, here I may have written wrongly. Like T here tends to infinity. After this limit, T tends to infinity. So in all the problems you apply this, you'll get the answer. So I gave some examples also where the energy for cos 2 pi SCT is infinity. Okay, because it is a periodic signal. Whereas power for energy signal is 0. And energy is calculated for a finite signal. That's why it is for infinity we have written, but it is only different for some certain period of time. So it is the finite signal. Then one question came on autocorrelation, the power calculation of the autocorrelation. So basically, autocorrelation is nothing but a similarity way of finding the similarity between two signals. Or auto means with itself. Okay. So suppose it is auto. So if it is the xt plus tau and xt, then you're calculating the average. Like you're multiplying and then you're calculating average. That gives a similarity score or the autocorrelation. And when you do the Fourier transform, it becomes a power spectral density. So whatever the thing or the calculation you have to do with the power, you have to do with autocorrelation function. Okay. And power spectral density. So this is how it looks. So power contained in random variable is equals to dx equals to minus infinity to infinity x of w dw. Why? When it is 0. Right? Which can be written as Rx of 0. So if we have function for Rx of 0, so whatever value is there, Rx is, so this is tau. This is the power contained in the signal x. Okay? That can be calculated using power spectral density as well. And we saw these types of questions perfectly. The next doubt was from week 8. Transform coding and all those things. You can you can give least importance to week 8. I don't think that there will be more questions from week 8. It's basically more generalization of autocorrelation and coding part. Okay, I'll go through the questions, but I covered the questions as well. I don't have here. I have to note that. Okay, leave it week 8. There was a question from this part. Which of the following is not a valid way of looking at the matrix multiplication? Did you ever see what is matrix multiplication? See, from the perspective of matrix multiplication, it's just a row column multiplication with sum. See this particular CIK. Will automatically answer this particular. So our correct answer is third. Yes. So yeah, there was a question asked by Ashutosh that what is the correct answer? Answer is two, second or third. So I can see in the mail. Its answer is third. Okay. It's a transformation of the rows of A by B. Rows are transforming by A by B. Okay. Because matrix multiplication is done in the sense that B to A, the rows of A are transformed. And these were the problems from the vector space. And there was a question on LTI. In time domain, it is a convolution, but in frequency domain, it is a multiplication. Moving to the next part. Decimation. Decimation and interpolation was covered. There was no question from the assignments. You can leave. These were the helpful MATLAB functions. I created this table for you. Uh, there can be some multiple objective questions. So you just go through this. Zeros, ones, I, rand. So just give it a look. And so many other questions were asked. Condition. You please remember these functions. It will be super helpful for you. What if you want to square it? You have to use dot, cap, square, two. Matrix multiplications. You remember some useful commands. 6x, float. These are some useful commands. I already covered, but just since this is summary class, so I'm just covering that. Length, B, these are some descriptive functions applied to two-dimensional matrices. These are not as same to vectors, okay? There may be some questions on that. Week 9. So signals and system was covered. Basic types of signals. Basic operations of signals. Convolution, correlation. You remember time reversal, time shifting, signal multiplication, integration. So if two signals are finite duration, then graphical method is used as function method is used to compute convolution. So try to remember this. System definition, simple. Classification, linear, nonlinear. Classification of signals, simple, invertible, non-invertible, stable, unstable. X is right equals to x square. The system will be stable because it is a bounded input, bounded output. Similarly, FIT is equals to integration of xt dt. Since it can go to any value, you even don't know what value it will go. So it will be unbounded for any stable input as well. So it is a non-stable system. So this is very important, this correlation correlation relationship. Uh, so the correlation the correlation or the correlation can be related as the correlation of any two signal can be represented as a convolution of one signal with a negative version of the other signal. Okay. So in that case, you can refer that. So these are some properties that you should know. So associative property, shifting property. There's some more descriptions. So correlation, correlation, relationships. You can see the example of this now. Sum of lower limits, area of convolve. We know that area of any signal is the integration of that signal itself. So here the DC component is area of the signal divided by the period of the signal. So there was a very good question on that. You can refer to this. Convolution can be calculated for the discrete convolutions as convolutive sequences A, B, C, E, F, G. This is how we can calculate using power spectrometers. Partial energy theorem, the energy calculated in time domain is equal to energy calculated in the frequency domain. Similarly, the energy calculated in time, power calculated in time domain is equal to summation of the Fourier square of summation of the square of Fourier coefficients. So Fourier series coefficients is Fourier series coefficient. So you have to remember that. And this is the uh, correlation can be written R tau. Autocorrelation can be written as a combination of X tau with X of minus tau. Okay. These are some properties that you may keep on mind. Just give a look on your chart. Analogy between vectors and signals. These are partial energy theorems. I hope it is clear.